well, it's 9:30, so let's get going. I know that they already have that thing turned on, so I won't do anything nasty today. So this one's about spatial data. And I have to ask before we start, how many people are actually doing spatial data in SQL Server? A couple? Yeah, 1, 2, 3, 4. Well, that's not bad, okay. I actually didn't know how many people were doing it. A couple of years ago, I did a talk on what's new in 2012 instead of spatial data. I talked the guy into it the night before and all. And people come and they go, well, where's the spatial data talk? So I figured it would work this time. So like I said, I've been working with this a lot, trying to do spatial queries go fast. My latest one, I think we broke the spin lock record at Microsoft. Basically, they didn't have enough threads in CLR. They didn't somehow generate it with that many threads. And so Guy has a 16 clock machine, and he's building this big spatial index, and it takes 2.5 days. And it's like, okay, well, you know, machines are cheap. That was all he was doing on the machine, right? So he goes out and gets an 80 clock machine, and the same spatial index build took 4.5 days. And he goes, it looks like the machine is sitting there doing nothing most of the time. Turned out the guy was right? It was spin locking against each other. And we just watched the spin lock count go and just go past the end, and go by again, and go past the end. They finally fixed it. So, spatial data was the big feature for 2008. They actually went out and got the best spatial guy in the world, I think, anyway. And he had implemented spatial data for IBM and for Informix, and they gave him just carte blanche to go out and do it whatever he wanted, the way he wanted to. So he did something that was unusual. Usually you have a geometry data type, and if you want to, project it against a map of the world, you just run the projections yourself, the mathematical projections. But he thought that projections were going to slow SQL Server down quite a bit. And so what he did is he instituted 2 data types, one for geometry and one for geography. And geography is the one that knows about the shape of the world. So it turns out that that's been such a big deal that some of the other databases like Postgres and all have copied that. But that was also, this feature was also one of the features that sold a lot of SQL Server 2008. So in 2012, they got some more money for it. So this is about the new 2012 features. If I'm going too fast and you want me to back out to the 2008 features, let me know. I did actually try and do the slide deck so that it would be continuous. Oh, never mind. You know who I am by this point, right? Okay, if you don't, there it is. And actually, that's what I was writing right here. So I did actually write the Spatial Index Internals chapter for Caitlin Delaney. She actually wanted a chapter on, in 2012, about the semantic search. And I said, look, I'll do the semantic search chapter if you let me also write about spatial indexes and XML indexes and full text search indexes. And she goes, cool, we don't have any of that in there at all. So anyway, there's a 60 or so page chapter that I wrote about all that stuff. And the internals of how it works, because it was interesting to me. So we're going to talk about better precision and curve support. That's new in 2012. More geography functionality. The big problem with geography in 2008 was that you couldn't have a polygon that was bigger than a hemisphere. Now, the first time I heard that, it's like, you mean overlaps both hemispheres, the north and the southern hemisphere? No, actually it's bigger than half the area of the Earth, right? You couldn't have a polygon that big. And then also, because they had the geography data type, they also had this concept of ring order. Because if you have a ring that goes around this way, if you have it in just geometry, you don't care. There's your ring and there's the outside of it. But if you have a ring that goes around that way in the geography, basically you have 2 choices, right? One is everything. Suppose you have a ring around the UK, right? Your 2 choices are, here's the UK, that's one choice. And the other choice is, here's everything in the world that's not the UK, right? So you had to put the points in the correct order in 2008. And so this was a big deal because if it didn't have the points in the right order, it would crash or it wouldn't load. And so in 2012 they fixed that, but that also means if you put the points in the wrong order, it wouldn't, it would load, but it would be sort of backwards. So I did a geography project on the animals on the Earth, and except for the whale, which actually takes up more than half the area of the Earth, I had about 100 of them that were actually too big. Like, it turned out that the polygons were in the wrong order. And this is because, and so what you do is just basically compare it to half the area of the Earth. And if it's bigger than half, then there's a method called Reorient Object, and I'll show you that. They also had sort of trouble with the spatial indexes when they started. Does anybody have trouble making up spatial indexes? It's sort of an art to do the spatial indexes. And the weird part was that the default was to take the space and divide it into so many medium level squares. And it turned out that that was not normally the best spatial index for much of anything unless you had sort of medium-sized polygons. So in SQL Server 2012, they actually made a new type of spatial index called the auto grid. And you have to tell whether the squares were low, medium, or high. Sorry, I'm getting, what do you call it, the air. Also, they put in some more spatial aggregates. So they hadn't had spatial aggregates in, and I'll show you spatial aggregates with map of the UK. And then some histogram store procedures. If you want to take a spatial area and say, let's see, in this square I have 1 point, and in this square I have 2 points, that's a histogram. And it's supposed to be usable for diagnostics, but I'll show you a diagnostic procedure from 2008 that I think is better. So the SQL guys from SQL Server had this slide forever, right? What is spatial data? What is it supposed to do? And they would read it every time, and that was it. Spatial data provides the answer to location-based queries. And so what I decided to do, well, I don't know, a couple of years ago, was to actually take these location-based queries and make examples of them. That sounded much better than just sort of pointing at them and spouting words. So basically, which roads intersect the Microsoft campus? So you do have to have what I call spatial reference data to do this. So if I want to know which roads intersect the Microsoft campus, I have to have a database that contains all the roads, or all the roads in the US, or all the roads in Washington State, something like that. I also have to know what the Microsoft campus looks like. Now I moved out when I did this, and I just took a ring around the Microsoft campus in Redmond. I didn't do the 5,000 Microsoft campuses around the world. So really all it's going to do is say, which roads intersect the Microsoft campus in Redmond. So here's the deal. And of course I had to find a thing of roads. Luckily for me, there was one out there. By the way, you can get spatial data, pretty much spatial reference data, for free in some countries. And it didn't used to be in 2008, but now the UK is one of those countries, right, that you can get different census data, you can get different geographic data, you can get places of interest. So it's out there for free. In the US, they had a law that said if taxpayer money paid to gather this data, then taxpayers were allowed to have it for free. So we got a lot of data for ours. Okay, so we're here, and spatial question slide. So there was a guy, in fact, he might even be in this, no, wrong mic. There was a guy that actually went and wrote something to allow you to look at a big map. Let's see if it's up. This is a long time ago, so it may not be up. Control-click to follow this. And I do have internet, so we'll see. And basically what this was a web page that gave you a map of the world, and you drew circles around wherever you wanted polygons, and it would generate you data for SQL Server. You know, it doesn't look like it's up anymore. But so what I did was I went out to his map, and I went to the Microsoft campus in Redmond, and I drew a polygon around it. Now, I drew a polygon around it, and this is the polygon. So now I have Microsoft campus, this polygon right here. By the way, by definition, a polygon is a circular thing that doesn't intersect itself, and the first point is the same as the last point. So unfortunately, people talk about polygons when they're going hiking. And if you go hiking and you intersect your trail, then it's not technically a polygon. However, SQL Server actually put some things in for that in 2012. They will do length calculations on what they call invalid geographies. So if you have an invalid geography, they'll still calculate the length. So this is the polygon things, which is good because I didn't want to make those up myself. And so that's the Microsoft campus. Now I can look at it and select it. And there's a nice spatial visualizer there. Because you probably guessed that, let's see, campus, that if I actually select it like this, no, that's not right. Select campus. It'll actually get campus in binary, and you would be correct. So here's campus in binary. And again, that's fairly useless to go, oh yeah, that looks like, the state of Washington to me, of course it doesn't. And if you go back and look at this text format, and by the way, the text format is called well-known text, right? Because that's a format that's actually a standard format that you use with geography. That doesn't really make any sense to anybody either. So what happens is, if you select the binary form, what they do is they give you in SQL Server Management Studio a Spatial Results tab. Now, don't get too excited about the Spatial Results tab. It's basically just a cheap one-off against the doneness map control. Somebody thought it would be good for visualizing things. And of course, the first thing that people say after they look at that is, how do I change the color? And the answer is you can't. So there's my campus. And again, it's not to scale compared to the roads. And now I have a database called Sample USA and a table called Highways. So I should be able to see which highways intersect the Microsoft campus. Now it turns out that if you select more than, I think it's 5,000 spatial rows, this thing just fails to work, right? The control, so you can't see it. So I'm just going to select the top 100 from highways. And because I have the binary form, you can see it here. There we go. That there's some highways. And actually, there's some pretty nice things you can do with these. You can hover over it, and it actually will show you the record values. But anyway, you could probably guess that that's the highways in the US. So how do I do that with a query? I want to find the ones from here that intersect over here. And of course, you could probably guess that there's a method called ST-intersect. And so ST-intersect returns 1 if the two things intersect, and 0 if they don't. So in this case, I have the highways table, and I have a column called geography. And ST-intersect basically takes a column here, a geography here, and a geography here. And so basically what I'm doing here is just going down through the whole table, looking for rows that intersect the campus. And if you've ever been to the Microsoft campus, there's a fairly famous for being as crowded as it is highway called the 520 highway, I-520. And that would help if I declared the value campus in them. So up here, there we go. No, I don't want the highways. Oh, come on. And so at the end of the day, you can get which roads intersect the Microsoft campus, and it's pretty quick. There we go. And so it's actually State Route 520. That's the one down here. So great. If you're from Microsoft and live in Redmond, that you will be impressed, right? So the next question on their slide was, so what else can you do with it? Well, how about, does my land claim overlap yours? Well, I don't have geography stuff with land claims on it. However, I do have, in the US, they have this thing called, legal body called Congress. And people vote for Congress by geographic area. And so basically I have all the congressional districts, they call them. And so what I want to know is those are polygons, and really land claim overlapping those polygons. So I have a Congress table and a zip code table. So rather than decide, does my land claim overlap yours, I'm actually going to look at the Congress table versus the zip code table. Because I thought one of these days I might run for Congress. And if I did, you actually get, if you're running for office, you get a, a break on the mail, if you send mass mailings. And so what I want to see is which zip codes I should include in my mass mailings. At least you can make that up. So, there, in Sample USA, actually I'm going to use a different one, census. In census, there's a Congress table and a zip code table. And so it turns out that my state is equal to 41, which is Oregon. And actually my district is 116. And so if you select this, it's rather interesting because if you know what the state of Oregon looks like, it doesn't look like this. Right, it looks like this. And so it looks like that awful thing at first because we're actually using, there we go, we're actually using geometry rather than geography. And the x and y in geometry is not equal to latitude and longitude. If you think about it, latitude comma longitude is not x comma y, it's y comma x. So do be careful with that. So there we go, now I've got the geography out there. And this is my congressional district right here. I live someplace around here. And so now I want to find out which zip codes overlap it. And actually pretty much it's the same query, right? So there's my zip codes. And the trick to making spatial queries run fast is you have it query as few rows as you can. Do anything you can before the main query to cut down the number of rows. And technically, that's what the Spatial Index does. We'll talk about that when we get to Spatial Index. So I tried to make it as fast as possible by having a common table expression that just selects out my district and call it my district, and then select that changing zip codes on my district geography intersects the zip code geography equals 1. And just to make sure it didn't bother with the other 49 states, I told it where state equals 41. Hopefully that'll make it run a little faster. And sure enough, it does. There we go. So these are all the zip codes that overlap my congressional district. And actually, I just moved. I'm in 97229. So if you get 97229, we're good. Someplace there it is. So that's it. Any questions about that? So the first one we did with actually an SD intersects with a table and variable. And this one we did with a join, 2 tables. There's one last one, which is, of course, find all the Italian restaurants within 5 kilometers of where I am. And so first time people look at that red and they go, why are you doing things in terms of kilometers? Don't you know miles? And that's because the geography data types actually have a definition, and it includes the unit of measure. And the unit of measure for all the big geography data types is meters, not miles. And so it's not even what we call kilometers, it's meters. So basically I want to find that. Now it turns out I don't think I have this one, the geonames on me right now. So the idea was, it turns out the geonames have a bunch of different feature codes, and one of the feature codes is restaurant. Turns out though, it's kind of disappointing, we only have 6 restaurants, and they're all in New York City. Right, that's what the mapping people sell for big money, right? They call points of interest. So there's only 6 restaurants in this whole thing, and they're all from New York City. So I decided to put myself in the middle of New York City, and then find the ones that are actually within 5 kilometers of me. So basically, this is important for that. And notice all I'm looking here is the distance between this column and me on a per row basis. And again, I could have, multiplied that times 1,000, but we're fine without it. Any questions? So that's pretty much the 3 spatial questions from the slide. Now, it turned out when I first saw spatial data, I thought, well, the only people that care about this type of data is people that make maps for a living. But I was soon, educated by the people that work with it, that actually spatial data is a part of every database, and you just don't know it. And what does that mean? Well, in every database, there's usually someplace, a city and a state and a street address and a postal code, and we just happen to encode locations like that. But if you actually encode those instead of in a city, state, and zip as latitude and longitude, you can do some interesting queries. Like, if I'm going to ship something to you, what is the closest warehouse to where you live? Or if I want to figure out how to get from here to here on the road system, how would I do that? And so basically, it's fairly easy, not tremendously easy, to actually call one of these web services, and it's called geocoding. Take the address and actually get the latitude and longitude. Now, if you were going to geocode things, there were people that started out at the beginning that said, we should geocode in a trigger, and I wouldn't do anything that hits a web service in a trigger. That doesn't sound like a good idea at all. You can either code them in bulk at the end of the day. I believe there is even an SSIS component to do this. Or you can actually spin off a request to service broker, and service broker can call these web services asynchronously. And by the way, let's see, the ones that I found were the Google web service. They'll actually give you as many as you want, as long as your thing ends up on the web. So the requirement for Google, because Google owns the web, right? So the requirement for anything Google for free is that if you write something, it has to be on the web, right? If you don't, then you have to get special permission or pay or something. Bing, on the other hand, Bing Maps will actually give you 1,000 free geocodes per day, but after that you have to pay. So anyway, it's not a niche thing, really, if you consider that anything in your database might contain an address. And if you want to do geo-based queries, you might want to change it to a latitude longitude. By the way, there is the capability to do the opposite too, take a latitude and longitude and make an address out of it, which is called reverse geocoding. So it's not necessarily a niche. Okay, so there's a specification group of people called the Open Geospatial Consortium, and Microsoft decided to go by the Open Geospatial Consortium spec. And actually the OGC defines spatial data in terms of an object hierarchy. And we don't really have the object hierarchy, but we have the spatial types that are supported by OGC. We have most of them. And so in 2008, here's the hierarchy. They support the ones in blue. So, and by the way, these are the ones that both Google Maps and Bing Maps support if you want to draw something on them. So we have point, and then line string and polygon, and we have multis, which are just collections of points, collections of line strings, and so forth. And then we have something over here called geometry collection, which can be a collection of anything. We'll see this when we look at the aggregates. In other words, a geometry collection can have 3 points and a polygon and a line string. And line string, by the way, is just a line with as many points as you want. Imagine a road as a line string. Everybody okay with that? So we support in 2008 the ones in blue. But this is about 2012 features. And so in 2012, they added 3 new features that have to do with curves. However, for some strange reason, I don't know why, I think they thought that their Open Geospatial Consortium was going to be replaced. They didn't implement these ones, right? Curve and surface. What they did is they went to another spec called SQL Multimedia. And the SQL Multimedia spec is part of the SQL, ANSI SQL spec. And so they're not called curve and surface. They're called circular strain, compound curve, and curve polygon. Now, why have these anyway? Because Google Maps and Bing Maps don't support them. What am I going to do? And it turns out if you do things in terms of curves, it takes less points to make a curve. You can make something that looks like a circle, right, with lines, but you're going to have a whole lot more points to do that. Whereas with the circular string, you can make a circle with 3 points, I think. That's the minimum you can do. So imagine 3 points versus 60 points. Also, if you're doing calculations, the fewer points you have, the easier the calculation is. So that's why they introduced these. And actually, one of the other reasons was because they could. Really? Yes, we can do these, and so why not put them in? They also introduced for Ed's the guy at Microsoft, for Ed's geography data type, they introduced a new type that's in nobody's spec. And the new type that's in nobody's spec is called full globe. And so full globe is interesting because it's the entire globe in, depending on what they call SRID you have. SRID is an abbreviation, stands for Spatial Reference Identifier. And so I want to show you some of these SRIDs. In SQL Server 2008 and in geometry, they let you use any SRID you want. They don't care. If it's a projected coordinate system, that's fine. If it's just a regular XY coordinate system, that's fine too. You have heard the term projected coordinate system before? No. I hadn't before. So I seem to know way too much about this now, but I hung out with these people for years. So it's just all fairly new knowledge, right? So what a projected coordinate system is in the US, and I believe they do that in the UK, but I don't know what they call it. Rather than have things based upon the Earth being round, what they do is they take a discrete place, like the UK, and they draw a square around it. And they make the bottom of the square 0, 0, and they make the top of the square whatever they want. And that's called the projected coordinate system, because it really doesn't have anything to do with latitude and longitude. In the US, they have one of these for each state, and they call them the state plane coordinate system. The weird part is when you go from one state to another state, you're totally lost, right? Or if you're trying to figure out how close is France, you're completely lost because they have a different coordinate system that starts with 0, 0 with some different place. So what's the one for the UK called? Anybody know? I used to know this. No? Okay, anyway. So that's geometry. And in geometry, you can use what's called spatial reference identifier you want. And spatial reference identifier is basically just a number so that you can say, oh, this spatial reference identifier code corresponds to a square around the UK, or this one is a square around the state of Kansas. And so they know what to do if they're actually going to try and put that together with the state nearby, or if they're going to project that onto a map. Right, maps are round, Earth is round, maps are flat. So because we have the geography data type, we have something that nobody else has, which is a full globe. And so full globe is kind of interesting because you can do things like how much of the Earth is water? And if that much of the Earth is water, then the rest of it must be, land. And so I wanted to show you an example of full globe. It's kind of cool. And also indicate, or sort of start with spatial coordinate systems. So I believe this is my blog about full globe, right? And basically with the Earth, You have different numbers, but the numbers actually depend on who's doing the survey of the Earth and at what point, and where they think Greenwich is. Apparently some surveys actually don't think 0 is Greenwich, right, the prime meridian, and how big they think the Earth is. And it turns out the shape of the Earth actually changes over time. They put like stakes in the ground, so when they came back they could see what the shape of the Earth was again, and it turns out these stakes have changed over time, like where they were. So to see what spatial reference systems, what SRID is, SQL Server supports, you can do a select star from spatial reference systems. But remember, these are only ones for geographic things. They're not the ones for projected coordinate system. So let's go ahead and try this. And what you actually get is all the numbers, and then what's the authority that made up that number, and what's the authorized number, because apparently it may not be authorized, and then what's the well-known text. Just like polygons and points and line strings have well-known text, the coordinate systems have a well-known text. And so let's pick this one out, just for fun, right? The font is so big that I'm going to have to copy it onto the page. But this is basically a well-known textual format that says this is a geographic coordinate system, not a projected coordinate system. And this one is named Greek. Oops, sorry. And they use something called the Greek datum. And basically what a datum is how big the Earth is, how wide and how tall. And it turns out, of course, the Earth is not a sphere. It's an oblate spheroid that sort of sticks out at the ends. And so basically, they define this in terms of whatever the ellipsoid is. Apparently, this spatial reference system was done based on a survey by a man named Bessel in 1841. And they think that the Earth is this wide, and they think that it's this high, in meters, I believe. And they think the prime meridian is Greenwich, and they think that the unit of measure is a degree, and this is how many degrees in something. Okay, so that's the well-known text. Now, that's nice, but nobody uses the Greek coordinate system apparently except in Greece. The one that we're going to be using, because it's in every GPS, is the one that's in the GPSs, which is 4326. If you use ESRI data, Esri data, they actually use another one, 4269, but they're fairly close to each other. You can almost, ignore the differences between them. And so 4326 is a little bit more modern survey. There it is right here. So when you make a geography, you have to tell it what spatial reference identifier you're using. So this is based, you can see, on the WGS 84 survey. And basically, there we go. It also thinks we're Greenwich and degree. It's a little bit different than this guy with respect to how big the Earth is. And that's the coordinate system we're basing it on. They call this the World Geodetic System 1984. So basically, if you have a cell phone, you are actually doing things in this unit of measure. And you can take the stuff from the cell phone and put it into SQL Server and do queries on it. Okay, so about the full globe. So what I can do for the full globe is actually make up a function called measure the globe. And what I want to see is how big it thinks the globe is. Now this is a function because I'm going to run it against every row, and basically I'm going to make up a geography, and from the well-known text, they had to make up their own well-known text here too, and they just call it full globe and whatever SRID you want. So you pass the SRID in and it tells you how big the Earth is, the area of the Earth. And what's pretty interesting with this is that they are all different. And by the way, I had to parse out the string to get the ellipsoid, so don't look, really stringy in my code. Okay, and when I do this select here, it's actually going to order by how big it thinks the Earth is. And this actually brings up, oops, what is it now? The special X included working with geography because it exceeds a hemisphere. I know, but this is 2012. Oh, Bettman, right, census, let's see what what version it thinks it is. There we go, so options, yeah, it thinks it's 100, version 100. So let's put this down to 110. I'm not using 2014, but I have to at least let it use 2012. And so now it's, notice that can be fairly irritating if there's a bunch of those that are like that. And for everybody else in the world that uses geometry, there's no requirement that the points are in a certain order. So most of the times they are, but sometimes they're not, which is why this is so good. Okay, so now this version works. There we go. And so basically what I've got is all these SRIDs are using the area in square meters of the Earth. But what's this thing? Well, this thing is actually a new SRID 2 in 2012. And what it is it's based on the fact that if I have the Earth looking like this and with all the mountains and valleys and stuff, it's going to be kind of hard to calculate things like the area. It's not going to be quick. So what they did was make up another SRID called the unit sphere. And if you pretend the Earth is a sphere, your calculations aren't going to be as good, but they're going to be fast. So you can pretend the Earth is a sphere. Notice it thinks these are 12.5, but notice they're measured in terms of radians. Everybody else almost is measured in terms of meters. And there's a couple of different ones. So this is the German legal meter. And there's somebody else that's using, where is it, Clark's foot. Because apparently Clark was a person who measured geography with his foot. Where is this thing? I swear. There it is, Clark's foot, right? And there's the US survey. Oh, and there's an Indian foot. Apparently, I'm not sure if that's, oh, that's Indian, not American Indian. Right, okay. So, and there's a couple that actually do use the foot. All right, fine. Right, and then this one is actually using radians at the top, which is why it's so far off. Okay, so that's the new SRID. And notice that when I go to 2012, if they have the database at the right level, you can see that they've removed the limit that geography instances can be more than a hemisphere. Because, of course, full globe is always 2 hemispheres. Okay. So imagine that they get it wrong, right? They got it wrong in 2008 and they actually had the ring order incorrect. So in 2008, I just get an error and there's nothing I could do about it. But in 2012, not only is there something I can do about it, but I'm not going to get an error. The thing is just going to be wrong. So they made up a new method called Reorient Object. And Reorient Object basically gives you the mirror image of the object. And I'll show you how this works. I've just been to Iceland when I wrote this demo. And so, where's Reorient Object? There it is. So I have a nice database. It's kind of small, called Spatial Samples, which I'm going to use later on. And it has countries and administrative districts. So here's Iceland. If I just go look for the outline of Iceland. And you could probably guess that that indeed looks like the country of Iceland. But if I call Reorient Object on it, it's everything that isn't Iceland. So here's everything in the Earth that isn't Iceland. And so, of course, that turns out to be a lot more. If you look really hard, the Iceland is at the top over here. There it is. Can you see it? The white's coming out. There it is. So that's Iceland. So Iceland and everything that isn't Iceland. But the nice thing about it now is that we don't get an error if we put in something that's the wrong ring order. But we do have to remember that we don't really want something that looks like this, right, if we're going to intersect it with anything else on the Earth. Yes, sir?
When you get that rectangle off the globe, does that approximate to the Mercator projection or the Peters projection?
Oh, you get to have your own projection. So I know this started out as like an afternoon project for somebody, and it turns out that you can choose your projection. Then the one that they choose by default is the equirectangular projection. So you can get a couple of projections in here. I believe Mercator is another one. So there's Mercator there. Now, if I do this with Iceland, at least Iceland will look different. Otherwise, we'll just get squares there. And so there's Iceland in the equirectangular, and there's Iceland in the Mercator, and there's Iceland in the Robinson projection. So you get a few projections if you want. Because you're right, maps are flat, Earth is round. How are you going to put a round Earth on a flat map? And now, actually, that you have computers, you can actually work like the Earth is round. Right? Computer doesn't care, it doesn't have to be folded up, right? Put in your pocket. Okay, so that's Reorient Object. Reorient Object is your friend. If you take a whole bunch of points and put them in SQL Server, one of the ways to check to make sure you don't have any errors is you just hit C, get a full globe, get the area of it, divide it by 2, and then compare the area of that to the area of your object. And unless you expect something that's bigger than a hemisphere, you can tell and just call Reorient Object on the ones that are all bad. Like I said, I had about 100 of those, but I did sort of have to adjust to the fact that the whale and the gray mouse, apparently, actually live in more than half the Earth. I think Ramos was this huge area. Okay. So data type precision. So if you read my talk about Windows Azure SQL Database yesterday, I kind of made fun of the fact that all of the updates to it, all the updates to SQL Server were going to be backward compatible, except for the first one they did, and they had to make a dynamic management view called things that will break on update, right? And this was the one, right? What they do is that the data type itself uses a binary format, the spatial data types. And if they construct one for you, in other words, they're not going to go through your table and recalculate all of them, but if they construct one for you, it uses 48 bits in 2012 and 27 bits in 2008 and 2008 release 2. Again, this affects constructed types only. What do you mean by constructed types? Well, besides whether or not something intersects 0 or 1, you can get the intersection. So if I have something that looks like this and something that looks like that, the intersection would be that spot down there. And the intersection is a constructed type. You have to make that type up. And so it only affects constructed types, not the ones that you have in your database already. But it is interesting that you can actually look to see if some of these two things intersect. And sometimes you'll get true, and then when you go to the next release, you'll get false. So here if I have two, G1 and G2, and I do a union of these, and then create a table that I'm going to actually use with this union. Oh, that's not good, it went away. Okay, there we go, table. And here's another G1 and G2 there. Notice that this is a constructed geography or geometry, right? I'm constructing G3 with a union of G1 and G2. These guys are never going to change, right? G1 and G2. I put in so many decimal places, and that's the decimal places I want. Leave those alone. But these ones are actually going to be better in 2012 than 2008. So in 2012, if I actually select these, well, where's the intersects here? Oh, you can actually see that they're different between 2012 and 2008. I'm not really actually doing an intersection. So, like I said, if you do go from 2008 to 2012 and you construct your own geography, bear in mind that they might be a little different. Somebody's actually come up with one that returns doesn't intersect in 2008, returns does intersect in 2012. That would confuse everybody. But they wanted to make them more accurate because if you put in that many decimal places, and you would, right, have to put in that many decimal places, then you want your stuff to be correct, and you don't want to lose decimal places. And what was happening in 2008 was the constructed geographies were losing decimal places. Okay. So, spatial types. So, spatial types basically have a lot of properties and methods. And I'm not sure if they should have done it this way, but rather than make, notice that the geometry has 89 methods, rather than make 89 functions that can only be used with a specific SQL Server data type, what they did is made a .NET user-defined type object. So everything that is using .NET. And all of these types are methods on the data type, like you've already seen. So there's 89 methods in geometry and 83 in geography. And you can tell the ones that are standard versus the ones that Microsoft made up, because the ones that are standard start with ST. And ST actually stands for spatial temporal. It's from the SQL multimedia spec. And so, okay, I can see spatial, what's temporal about? Well, you've seen a moving weather map, right? If you put the time in there and you know where the clouds are, you can see them move over time. So this is the spec for spatial temporal data. Of course, you don't have to have a time if you don't want to, it's optional, but you can have one if you want. So all of the ones that are compliant, like ST intersects, those start with ST for spatial temporal. All the ones that Microsoft made up, like Reorient Object, those don't start with ST. That's not a standard method. So SQL Server specific methods do not start with ST. And there's a couple of them in there that are extensions. Geometry actually is completely standard. It implements all the OGC methods, and that's one way to see how standard things are. Whereas notice geography is a little bit different. And there's some methods that actually apply to geometry that don't apply to geography. One of them, for example, would be to get the midpoint. And a midpoint is fine in geometry because everything is flat. But you don't really get a midpoint in geography because things aren't flat. You have to take the curvature of the earth into consideration. And so for geography, they don't even implement that method. Instead, they implement one called envelope center, and it'll basically draw an envelope around your thing and get the center of it, as though it was not a flat thing. Okay, so this sort of leads into the new methods. So actually, it turns out that there's 8 methods that you would use to compare one geometry or geography with another, and geography didn't have some of these methods here. And besides ST-intersects, which you've already seen, there are about 7 more of these. And geography didn't have 4 of them in 2008. And the 4 they didn't have, they added 3 of them. ST within, ST contains, and ST overlaps. It's fairly strange too, because if you look at the definition of these things, overlaps actually mean, does this overlap that? On the other hand, if they're exactly the same, so the first one is the same as the second one, overlaps returns false. And somebody on Twitter said, that's a stupid thing, who thought that up? And it's like, did Microsoft mess up this implementation? It's like, no, that's the way it's defined by the Open Geospatial Consortium. They also, and these ones can use the spatial index. Again, if you can use the spatial index like ST-intersects does, it's very nice. And if you don't, it's going to take a long time. They also have one called ST-convex hull, and I'll show you a convex hull aggregate coming up. Now, it turns out that, remember I said that if you walk around and you try and make a polygon of where you walked in your hiking, and you overlap your own hike, that's not going to be a valid polygon. And so you can see if something is valid, and starting in 2012, you can actually make it valid. Basically what they do is take the polygon that encompasses your hike, and they make it into 2 polygons at the intersection point. So they make it into a valid geography. And again, we saw Reorient Object. There's a couple of other methods on geography and geometry. One is shortest line to. So basically imagine I have a square, and I have a point over here. When I say the distance between something, right, if I ask for the distance between that, it has to be the distance to one of the vertices in the square. Let me show you. Sorry, you can tell my voice is going. Here's the shortest line to versus distance. And actually, this is a point within the same. So if I have a geography that looks like this and I have a geography that looks like that, I can actually select things with union all. Right, and union all will actually show me both of the things in the picture at the same time. So here's a polygon and here's a polygon. Right, now if I was to actually look for the distance would be from here to here. If I'm actually calculating distance, it has to be one of the vertices of that other one. But if I'm looking for the shortest line to, the shortest line to is from here to here. And so basically you can get that rather than just have to use a vertice. And by the way, this ST buffer is basically to make a line show up, right? Otherwise you get this little bitty line that you get really thin that you can't see. So ST buffer just basically draws a buffer around it so you can actually see the line there. So there's the line from one place to another. Everybody okay with that? And the bigger you make the buffer, the less it looks like the line. Okay, so the shortest line too. Also, because they added 4 new data types, the circles and the full globe, for each of these data types, you can find out the minimum DB compatibility level. Because if you try to do what I did and use full globe against the 2008 database, it fails miserably. So you can find out before you do what's the compatibility level you need to do this. In 2008, you couldn't do that. In 2012, you could. And again, ST length works on invalid line strings, so you can actually measure the distance of your hike where you might overlap yourself. Because basically, even if you make it valid, you're making it into 2 circles. And I want the distance around from one place to another where I've overlapped myself. So for GPS data, he actually put this in. Normally, if you try and call a method on an invalid type, so if is valid equals false and you call a method on it, it returns null. So this one will actually return the right thing. And we did this specifically for GPS and for roads and things like that. Okay, there's some more new methods like buffer with curves and number of curves and so forth. And there's also the Z and M properties. So if you think of geometry, geometry has X and Y. If you think of geography, geography has longitude and latitude. Remember, longitude is X, latitude is Y. But there's actually 2 more coordinates you can have, Z and M, or Z and M. And Z is actually the height of something. So if I want to take a vacation to the mountains, and I want to figure out how long it takes me to drive there, I don't want to know the distance between me and the middle of the mountain. I want to know the distance between me and the top of the mountain. Now it turns out they will let you put these in, but these aren't considered when you do spatial calculations yet. So you can put them in and you can graph them, but if you actually ask for the distance between me and the top of the mountain, you still get the difference between me and the middle of the mountain. It turns out that they were hoping, I don't know why they were hoping this, they were hoping that somebody would write them a 3D library. Like, okay, maybe they could buy one at the store, right? Now, besides X, Y, and Z, they also have M. And M is a weird one. It's sort of a wild card thing that you can put in there, and it means measure. And you can put whatever measure you want in there. So conceivably, if you want to, you can put the number of minutes past midnight in there, and that would be fine for spatial temporal. It's totally up to you what you put in as M. So most people don't have C and M in their geographies or geometries, so now you can actually ask if you have one. And to put it out as binary doesn't include Z and M, but you have them, it's just not going to do calculations on them. And so there's another method called is binary Z and M. Imagine we did all 83 of these silly things. Okay, but these are just the ones they had in 2012. So using spatial with .NET, one of the nice things about having spatial data types in SQL Server be .NET based is you can actually use them on the client side as well. You can actually take the binary form, push it back to the client, and on the client you can do some spatial calculation yourself. Now it turns out that's not going to be as fun if you're trying to do that with Java, but if you're trying to do that with .NET and it already is .NET, that's fine. So what happens is that spatial types actually live in a .NET library called Microsoft.SQL Server.types. The nice thing about that was whenever I had any problems with the spatial types, I could take that library and run it through the disassembler and see what they were doing, right? The Redgate disassembler or another different one. Now it turns out though, they're not completely in those types because for speed, they're actually implemented in C or assembler. And so there's actually a DLL that lives in Windows System 32 that they call from the .NET facade. So you do have to remember to install both if you want it to work. And basically the easiest way to do this is to go out and get it off the web, and it comes with an installer from the web, and you can install both. So you don't even have to have SQL Server to be able to do these things. So the library is useful on the server and on the client, and on the client, these things are called SQL geography and SQL geometry. And I forget what the reason for this was. Oh, they wanted to call them this everywhere, but it turns out there's a, what do you call it? Standard that says you can't call SQL data types things that begin with SQL. So they kept the data types called SQL in the library in .NET, and in the SQL Server they actually show them as geography and geometry. Now, this is sort of a nice library because it also contains something called the Spatial Builder classes. Somebody says, well, if I build them with SQL, I'm going to have a cursor, and I'm going to have to build them one at a time, and it's going to be a pain, and indeed it is, right? So there's a set of classes in here called the Spatial Builder, and you can write stuff in .NET either on the client or you can write a .NET Stored Procedure to build stuff for you. One of the things I did just to try and figure out how hard it was to actually try and implement all the Oracle data mining spatial methods or features in the SQL Server. And actually didn't turn out to be that hard. I did need SQL in a couple of places, but most of the time I just did it in .NET. It was relatively fast. So let me show you these Spatial Builder classes. Spatial Builder classes are the quickest way to build spatial objects from a series of points. So of course I have .NET someplace over here, and just for fun I decided I'd build a multi-polygon. So basically the way that you do this is you write something that returns a geometry or a geography. You call whatever you want. And then you start off with a Spatial Builder instance and new one up. Set the SRID that you want. Notice I'm building geometries, so it's perfectly valid to set the SRID to 1. I can set the SRID to anything I want for a geometry. And then start the collection by calling begin geometry. And start the first element by calling begin geometry. So basically what I'm going to do is I'm going to have a collection of more than one polygon. And so this is the one that begins the set of polygons. This is the one that begins the individual polygons right here. And then basically you have to say begin figure and give it the first point, and then start to add points one at a time with this add line. When you're done, then you can call add figure. And basically what that does is that completes the first polygon. And then this gives you the second polygon right here. And then you call end figure and end geometry. Pretty easy, right? And once you've done that, oh, here's another polygon. Okay. Here. And finally I ended over here. And what you end up getting from your GB, from your builder, is actually something called constructed geometry, and that's what you return. So basically, if you're going to do some quick calculations to create objects, it's better to do it this way than it is in SQL. And it's pretty easy to write these things as .NET Store procedures using find functions. Any questions for that? Now, this has been around since 2008. So in 2012, remember, we got some new types. We got circles and we got full globe. And so what they actually did was it's built on interfaces, iGeometry Builder and iGeography Builder. And in SQL Server 2012, they actually have iGeometry Sync 110 and iGeography Sync 110 for 2012. Right, the original one was 2008. And they add another method called deserialize, which is kind of nice. It takes it and it breaks it into a set of points. Any questions about that? So that's new in, or at least this part of it is new in 2012. Okay, we're almost at the end. This is probably the most fun part. So, spatial aggregates. So starting in 2005, you can write your own aggregate in .NET. And very few people do this. As far as I know, I've written a couple in 2008 and some in 2005. But the spatial people thought it would be really good to have spatial aggregates. So they wrote these in .NET in SQL Server 2012. And I wanted to show you how they work. Okay, we'll go back here. And we're going to actually do this with the administrative regions of the UK. So if I use this database, here's basically a composite of rows where each row contains a district of the UK. I think there are 4 of them. Yep, there are. And if I go ahead and look in the spatial results tab, you see that. They're all different colors. So that means I have one geography for each district. So now what I can do is I can start to put these things together. So union aggregate, so select geography union aggregate, basically is going to make them into one geography. Remember here I had 4, now I'm going to have 1. And you can see it that way because it's all going to be the same color. There we go. So it actually unions them together, and the outside ring there is actually going to be the outside ring of the whole thing. There's also the envelope aggregate. So in this one, again, if you want to project a bunch of points or roads or something over a map, if you have a map and you have a bunch of roads, you can just project them with union all. Union all works good. So what I'm going to do is I'm going to take these geographies that I had before, and same ones, and then I'm going to union them with an envelope aggregate. Now envelope aggregate is actually going to do what you think it does. It draws an envelope around the whole thing. So what we'll see when we do this union is we have the originals underneath. There's the originals. And there it's actually drawing the around the same thing. Now when I first looked at this, I thought to myself, well, it looks like there's got a lot of slop in there. But it turns out it does actually go as far as here. And with geography, because they assume that the world is mostly flat, it won't, I'm sorry, mostly round, it won't look the same as if they did it with geometry. Any questions about that? So again, we start with our administrative districts here. And notice that we have 4 rows over here. Right here. Now, remember when we did union, we took the 4 rows and we actually put them together as one row. So let's go back to our union again. And in union, we'll see, there we go. Let's call toString to see what kind of geography I have. There. So with union, you actually get 1 row. but the geography name is multi-polygon. Whereas with this one, right, the collection aggregate, you actually get a geography collection rather than a multi-polygon. There. So that's the only difference between the two. And notice they get a geography aggregate of exactly one multi-polygon. So the collection aggregate gets an aggregate collection. One last one. So there's something that's similar to the envelope, and that's the convex hull. And you'll see how different they look from each other if I just do this. So convex hull is actually going to try and draw a shape with the least amount of slack in it. Notice that it looks like this shape is sort of a envelope around everything rather than around it in a circle or in a sphere or in a spheroid. Everybody okay with that? Okay. Now it turns out that somebody said, well, how do you use these in a .NET program? I want to actually be able to do these in .NET. I don't want to be able to do these in SQL Server. And it is part of the library, so you should be able to use them. Well, if you've ever written an aggregate in SQL Server, how am I doing for time? Not bad. If I'd ever written an aggregate in SQL Server, you know that the way you write an aggregate is you write a class that implements 4 methods. And the methods are initialize, terminate, and what's the other one? Accumulate. And there's a 4th method called merge. Merge is if you run the aggregate on multiple threads. You can merge the 2 threads together. So basically, if you want to call this in .NET, how they implemented it was in terms of initialize, accumulate, terminate, and merge. We're not going to use merge. So what you do is you can write your .NET here and call the spatial aggregate. And what you basically do is, I'm going to make a spatial aggregate, there it is, of a type geometry union aggregate right here. And I'm going to aggregate these 2 polygons together. Now, unfortunately, I don't have this in a nice GUI map control, so you won't see anything wonderful. But what you do is you call init for the beginning of the aggregate, and then for each geometry in the list, you just call accumulate. When you're done, then you call terminate, returning the answer, which is itself a geography. And that's basically the way this runs. If I was to actually compile and run it, you say, it would be nice if you stopped it at the very end. What's that? Let's control like that. It's been a long time. There we go. So there's my answer is polygon that looks like this. Everybody okay? And what were we doing? We're doing union aggregates. We took 2 polygons and made them into 1. Okay. So that's how you call those in .NET. So one of the things I happened to just struggle with forever was the spatial indexes. And so in order to make things run fast, you have to have a spatial index, and you have to have the right spatial index. So I'm going to talk about things that are in 2008 and in 2012 as far as spatial index is concerned. Now 2012 does have some interesting enhancements for spatial index. One of them is you can compress the spatial index, which is actually good because these things are huge. So the spatial index is actually based on B trees. In fact, let me show you how it's implemented. If I go back to SQL Server Management Studio and I go to my census database, there's census, I should be able to find something that has a spatial index on it. And by the way, the full text search index, the XML index, they're all implemented basically the same way. So, not with spatial obviously, but with XML or whatever. So in census, I have a table called let's pick one out, Congress table. Okay, so there's the Congress table right there. And if I say select start from Congress, well, you know we're going to get our aggregate as that. Right, we're going to get it as a binary. Okay, so the way the spatial index works is it takes either the world or a bounding box. What's a bounding box? A box around one of your spatial features. It takes either the world if it's a geography or a bounding box if it's a geometry, and it actually cuts the box into squares, and this is called tessellation. I actually had to look it up in Wikipedia. It is got a Q, right? Wikipedia tessellation. It's not a spatial specific thing, but you can actually see, it's a nice picture of it. It's basically the same as tiling. You divide things up into a number of tiles. There's tessellation. But all of our tiles are square. except if we have geography, then they're sort of weird looking. So take it and divide it up into squares. Okay. And so what we end up with is something that looks like a picture of this right here. Notice that we have 4 levels in our spatial index in the SQL Server 2008. So the spatial index is actually tessellated, and it's also hierarchical. So imagine taking the world and dividing it into, is it 16 squares, and then taking each of the 16 squares and dividing them into 16 squares, and then you do that 2 more times. You're going to get a lot of squares. Now, if you wanted to use geometry, and you just wanted to draw a square around the UK, you could get a lot finer squares, right? You could get a lot of squares that were smaller. And the idea with this is that you tell it how many squares to make. But here's the implementation. Basically, each of these squares is a binary representation of what the square should look like. And what they do is for each of your spatial features, do I have this? Here, let's see. There we go. So this spatial feature right here, right? That actually covers what? 1, 2, 3, 4, 5, 6, or 4 times 3 is 12 squares. Right, now one of the squares in the middle, this one right here, it covers completely. This one's actually covered completely too. But these ones are covered very little. And so the premise is that they make a table, and they break every one of these spatial features down into a series of squares. And then basically what they do is just put out a table that has the square number, and whether or not it intersects, or whether it completely covers, or whether it just overlaps at the edges. Everybody okay with that? So you can see this. Once I saw this, it's like, oh, okay. So you saw my spatial there. Let's actually go and see what the Congress index looks like right here. And the Congress index, is there a spatial one? Oh, good, okay. Geography or geometry Congress. So we actually can't look at them like that. Microsoft tries to hide them from us. But we can, indeed, go and look at what's called the sys-internal tables. There. And if we show sys-internal tables, we can see that for each spatial index, you have one of these things. Extended index, and this is the name, the number of the table, and these start at 64,000 and go up by 1 each time. Everybody okay with that? So let's actually just take one. We don't have to take the Congress one and see what it looks like. Now, the problem with these special tables is you can see that they're there, but you can't see what they look like. So the only way to see what they look like is to actually log in with a dedicated admin connection and do that. So here, they're actually all in the schema number 4, which would be the sys schema. And if I said select star from sys, and then give it the name of this extended index, there we go. Then you'll see that they know it exists, but they won't select it, right? It says invalid object name. And you know and I know it's invalid. It's valid because we just saw it there. So what you can do is log in with a dedicated admin connection. The way you do this is change your connection. Remember, you only have one of these. And if you do this, the database administrator is going to get upset because that's her connection, right? So don't do this when they're around. And what you do is you put inside before your name of your machine, admin, and basically admin colon. And when you do that with admin colon, it gives you the dedicated admin connection. Now, it lies, right? It says failed to connect to SQL Server. The reason why it lies in 2012 is because IntelliSense also takes up the connection. And you can only have one of these at a time. However, notice that the thing is now changed to the master database. And if I change it with the use command, notice I can't change it by this thing. But if I change it to census with the use command, there we go. Now it'll change to the census database. So indeed I am connected. And let's see it. There. Wasn't that fun? So each of those squares has what's called a cell ID. And basically what they do is they number the squares according to, oh, I forget what's the name of the guy, a pattern that he made up. And then the cell attributes is whether or not the spatial feature covers the cell completely, covers part of the cell, or intersects the cell at the edge. And it makes a big deal of difference. Notice that you can tell which is which because this is the key for key number 81. This is the one for 62. So spatial index are basically what IBM calls side tables. right? It's a table that has some information about another table, but it's completely separate from this table. However, notice that this spatial index right here doesn't contain the spatial data, right? There's no spatial data in there at all. There's cell IDs, and there's primary keys so we can get back to the real spatial data. So what happens? Almost all of the spatial query plans look the same. What they do, and the spatial index is meant to be, it's meant to get rid of most of the rows. So imagine that you have, goodness, a row for each city in the US or each city in the UK, and you have a point. Basically, you can get rid of almost all of the cities if you have a good enough spatial index. And the goodness of the spatial index is measured in terms of, can I get rid of 90% of the rows? Can I get rid of 95% of the rows? Can I get rid of 99% of the rows? Something that only gets rid of 30% of the rows is a pretty bad spatial index. And here's why. So suppose I was going to do that query that I had before. Right, this one right here. Goodness. The spatial questions. And remember, I was using the Congress in there. If I actually go ahead and do this and look at the query plan, it's going to show us spatial query plans. Now, it turns out spatial query plans are pretty much all the same. Right, there's 3 different spatial query plans you can have, and that's it. So there we go there. There's the execution plan there. And so I'll just read you the spatial query plan really quickly. Actually, we have a whole 20 minutes. Right? So, of course, I only bored one person out of the room, right? But besides that, I'm sure everybody else is riveted to their seat, right? Well, the idea is if you can solve these, there's bucks in this, right? I mean, it depends on how many people are doing spatial, but this is what I did for the last 3 years of my career that I worked on actual work, right, is to try and solve these. Because basically, if you have the wrong index, it takes minutes, and if you have the right index, it takes seconds. And if you're staring at a Google or Bing map, you don't want it to take minutes to come back. Okay, so let's read it actually top to bottom. So this seek is because this is basically a join. So we'll leave this seek out of the Congress table. And what they're actually going to use is they're going to use the spatial index of the, and how can I tell which one it is? They're going to use the spatial index of the, can you see which one it is? I can't see which one it is. The other table then. Where's the other table? Actually, you can see it's the zip code table. Here we go. Whoops. So it's going to use the zip code table further on. So when it's finished figuring out what zip codes there are, then it's going to join it to the Congress table. Okay. So if you start at the right-hand side, what they do is they actually tessellate every value that you put in. So they do this with an internal function, which you can look at if you disassemble it, called getGeography tessellation. And getGeography tessellation basically takes each row in the Congress table and tessellates it, because the one we're going to use is the index for the other table, zip code table. Now it turns out, even if you had a spatial index for Congress and exactly the same shape one for zip codes, they can only use one at a time. So unfortunately, you have to tessellate one or the other. Okay, so there's the tessellation right there. They're taking the Congress and breaking the Congress and actually breaking it down into squares. And they have the same shape squares for those as they have for the spatial index. Remember that that's a hierarchical index as well. If you look at the index rows, the hierarchy part is actually encoded into the binary cell ID. I actually let you take this apart if you listen to the book chapter. So what they do is they have a constant scan that actually scans 4 levels, and they join all these 4 levels together and aggregate them. And so at the end of the day, what they have is a spatial index which contains these rows, and a spatial feature that contains these rows, or a spatial table that contains these rows. So you can see that once they've got through the hierarchy part of it, they do an interloop join between the spatial index's cell IDs and these guys' cell IDs. Everybody okay so far? Okay, fine. So the big problem at this point, we have our join, and actually our join only has 1,200 rows in it, so 1,200 possible rows. Notice that, by the way, if you ever look at spatial indexes, don't look at the estimates. And don't use a, what do you call it, estimated plan. The SQL Server Query Optimizer team knows absolutely nothing about spatial geography. And so therefore, the estimates are just way out of space. You unfortunately do have to use an actual plan and the actual number of rows. And if you want to see why something's so outrageously wrong, in other words, if you chose the wrong plan, then you can see how much different this is to that. Believe it or not, that's not actually so bad, right? So out of 32,000 rows in the zip code table, they've eliminated all but 1,200 of them. Good. The only problem we're at now is once they've aggregated them over the hierarchy. The problem was, like we said before, that the spatial index does not contain the geography. Oh, so what we have to do, and this looks outrageous to most people that do query plans too, but it isn't, is to actually go and for each row, for each what they call candidate stuff, for each what they call candidate row, right, one where it might intersect and it might not, they do a seek. What do you mean it might intersect and it might not? Well, if you go look at this, if it's in this particular square over here with the green, if it's here, it's not going to intersect. But if it's here, it will. So basically, they have a set of candidate rows, and you can probably see the optimization they make here. If you have the fact that this particular thing covers an entire cell, they don't have to ask, right? The answer is always true. So, point over polygon query, right, where you're saying, which polygon does this point live in? They can usually do this as an optimization, and they never have to calculate intersects. Goodness, if my throat's something like this, it sounds just really horrible, right? Okay, anyway, at least I'm still able to talk, right? So this is nice, and this is actually what you aim for. So the way you aim for this is to make those squares as little as possible. So there's a lot more that would cover any spatial object. Everybody okay with that? So let's just drop back a little bit. For each of these levels of tessellation, you can specify low, medium, or high. Low is 4 by 4, medium is 8 by 8, and high is 16 by 16. So the default is medium, 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 medium. Actually, this is a low, 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 low one because I can't put it, it wouldn't fit on a page otherwise. Okay. So now I'll go back in. This is the part that upsets everybody, right, that does query processing, is that I have to do 1,200 seeks. And usually people don't like to do 1,200 seeks. With the spatial index, it's worth it. And so what they do once they've done those 1,200 seeks is this filter here is actually the thing that runs, where is it? ST intersects, see it? It's right here, right? It's running ST intersects, but it's only running ST intersects if you don't completely overlap the cell. If you completely overlap the cell, then they just forget about that and return true. Now, the reason why they go through all this nonsense is that ST intersects is a tremendously expensive operation. And if you didn't have a spatial index, what they'd have to do is what? They'd basically just do a scan on everything and do ST intersects for every single row, right? And the difference is amazing, right? The difference is the difference between, say, 1 second and 3 minutes for a spatial query. So the index, over time, the query optimizer people have always underestimated the goodness of the spatial index. And so what I actually was able to do was, and you may have seen these are the query transformations that they do. This is DM, it's like way off. Oh, nice, okay. Query transformations. I'm looking for IntelliSense, and IntelliSense goes, I don't know you. There. No, yes again. Sys DM exact query transformations. I don't know what's wrong with that. Anyway.
You still connected through that special.
Yeah, but you should still find them. But yeah, I always forget about that, right? All right, one chance, and I'll tell you what I was sort of going towards. Sys DM exact query transformation stats. What is it upset about?
Your SOTs on the other one?
Query transformation. Oh, thank you. I looked at that and I didn't see it. I'm glad you're here. Okay, there. So if you've seen these before, or if you haven't seen these before, you can be impressed, right? Here's how the query optimizer works. Basically, the query optimizer starts off with a naive plan, and at each step of query optimization, it has what's called so many moves, or so many transformations. And basically, these are a set of transformation rules. Some of these rules are actually implementation rules. So this said, in my query I coded a join, I'm going to implement this as a nested loop join. And so what these rules are is actually COM components. And what they do is, if they consider using this rule, they actually call into the COM component and get what they call a promise number. What's a promise number? It's how promising this is for this particular query. Now this thing is cumulative, but you can actually take it apart and get them for specific queries. So the higher the promise number, the more likely they are to actually use that transformation. So here's the big bragging thing that I was going for anyway. So I said the query optimizer people really don't ever know the goodness of the spatial index. So here's the spatial index filter over grid index. That's the one that actually decides whether you use a spatial index or not. And over time, we actually had them pump up the promise number quite a bit. It's like it should really use the spatial index almost all the time, because you just put the promise number higher, and then it would use it by itself. Right? If it doesn't use it by itself, you can actually put it in as a hint, right, once you use the spatial index. Everybody okay so far? So let's finish off this query plan. Oh, we got 15 minutes. And then I'll finish off the slides, which there aren't very many of, and then I'll take questions if you have any of them. How could we possibly have any questions? Well, if you're not asleep, which you're not so far, this is good, you might. Okay, so again, I had 1,200 that matched. I went back and I got the main row for each one with a C, so that I could decide whether or not I wanted to do this estimated test. The goodness of them is how few of these I have to do. And unfortunately, this is a case statement, so it doesn't tell you how many you have to do and how many you don't, which is kind of a bummer. And then after that, they basically join it to the other table and they get the answer. Really? Yeah, really, here it is. Right, and how many did they think there were? There were 1,200 candidates. And how many do we actually have? 72. So actually, 1,200 candidates with 72 actual rows is not horrible. And actually, remember, in this case, we're not doing point and polygon. We're doing polygon overlaps polygon, which is harder. So how do you decide which spatial index you want? By the way, let's get back to 2012. What did 2012 add to this? Well, before 2012, all the indexes looked like this. And you had to yourself select small, medium, or large. Gracious. Small, medium, or high for every single one, right? Low, medium, or high for every single one. And this turns out to be a big part. Like I said, I did this for 3 years. It's not fun. And the only thing you can do is sort of guess, see how long it takes, guess again. By the way, if you're doing point and polygon, high is always the best, right? Obviously. You make little bitty squares, they overlap, you're all set, right? Okay. So what they added in 2012 was a different kind of spatial index, because nobody wanted to play, let's guess how big we should make this, right? Especially the people that do spatial for a living, they just wanted to say, let's put an index on. And so the spatial index they put on, by default, was something called an auto-grid index. And what they did with the auto-grid index said, this is the general best index. So if you want to put this on, and you don't know which one to do, and you don't want to hire Bob to go play with it for a week, you can go and say, I like that, please, the auto-grid index. Now this is kind of strange, because remember the other one were 4 levels? This is 8 levels. And the density is always hard-coded at the top level is high, and then the rest of them is low. Now, by the way, what's the cells per object? I sort of skipped blithely over that. Well, skip blithely over that was this. Oops, I'm going down here. It's back. So notice that at this level, I have 1 cell. At this level, I have 1 cell. At this level, I have 2. At this level, I have 12. For each spatial index, you can tell it how many is the maximum number of cells per object that I can use. So say, for example, I say that the max cells per object is 128. Then I can use the itty-bitty squares. But suppose that I say the maximum number of cells per object is 4. Well, I get one of these, maybe this one, because it doesn't hardly overlap anything, and then 3 out of here. So it's the number of cells that you can have per object. Obviously, the bigger that number is, the bigger your spatial index is. Right, so that's the cells per object. And what's this deepest cell rule? Well, if this deep cell is covering everything, then they'll do that, else they'll drop back 1 level. Else they'll drop back 1 level for that. Everybody okay? So if they had max cell per object equals 1, they would do this one. And if they had max cell per object equals 2, they would do this one. And if they had 8, they'd have to have sort of a combination of some of these and some of those. Okay, now you're all spatial index experts. So what did they add? The auto-grid indexes, right? And the cells per object is hard-coded, but you can specify them. They also put compression support in there, and they put a spatial window max cells hint. What's the spatial window max cells hint? That's for the tessellation step. Remember, if I go back to the query here, and I go back to the query plan, and they said you were going to tessellate these? Before, they always allowed up to 512 tessellation rows per object. And so now you can actually choose how many rows you want. Again, it's an esoteric thing, but now you know how it works. And they finally came up with an optimization for something that everybody's always wanted to do forever, which is the nearest neighbor, right? The nearest neighbor is basically, here I am, tell me where the 4 closest restaurants are, right? And so there is an optimization for that as well. It is a kind of weird query, and it does produce a different query plan. I'll just show you the query because we're getting late here. Okay, here's the nearest neighbor optimization over here. They add an actual couple of steps for this. Where's the nearest neighbor? Oh, right there. Okay, there. So if I create a spatial index over here and create a spatial index over here, here's the nearest neighbor query. So basically what I want is top 7 nearest neighbors from person address. So there's a person address field in AdventureWorks. By the way, if you ever look at person address versus a map, they're not real addresses, right? If they were real addresses, you'd get sued, right? So they're fake addresses. First time I tried to find these guys on a map, it's like, where is it that they live? Oh yeah, these are fake people. They have to live in fake places, right? So I want the top 7 persons that live next to me. So I have a top clause, but a top clause isn't enough. To get this optimization, you have to have a where clause. And you have to have a where clause that includes a distance. And the distance can be a specific distance, like 1,000 meters, or the distance can be is not null, right? And that'll actually use the spatial optimization. Do I have one here in AdventureWorks? It's basically just a little different plan. Oh, I said I wasn't going to do this. I will not do it. Okay, in AdventureWorks 2012, if I go ahead and do that, so let's try it. Oh, and of course, as soon as I change the window, it's going to be, no, good. I was going to get upset about the dedicated admin connection. So what are the 7 closest people to me? And notice that that was fairly good, believe it or not. The nearest neighbor queries in 2008 used to take minutes to do nearest neighbor query. And actually, there was a guy named Isaac Kunin that actually wrote an outrageous formula to do nearest neighbor that works really well in 2008. K-U-N-E-N, and he's got a blog entry that has this formula. But anyway, there's the 10, these 7 people that live near me. Okay, so we have 5 minutes left to go. Come on. So there's various optimizations in all parts of spatial to make it run faster, and the aggregates are more performant than they used to be. And there's the index diagnostic procedures. So basically what an index diagnostic procedure looks like is you run something against an index. You run XML against an index. I've given you some of these, but it's sort of too late to do one now. Here's the diagnostic procedure code right here. And so what you do is you create a spatial index, and then you run this thing that's called, there it is, SP help spatial geography index XML. You give it the name of the table, and the name of the index, and the name of something that's called the query sample. A query sample is basically a usual row from the other table, or a usual thing you'll be querying against. And what it does is it produces XML as output. And so they've had this in 2008 too. Here's the one with all high index. When I see the XML, it actually shows me information about the index. And then what you're really looking for is this right here. Internal filter efficiency and primary filter efficiency. Notice this is e to the +1. So basically this isn't a wonderful index. It filtered out 50% of the rows. And by the way, what's the primary filter and what's the secondary filter? The primary filter is the one that filters out the rows. The secondary one are the ones that say, hey, it covers the cell. I don't even have to ask, right? That's the secondary filter. So what you're trying to do is you try and start with a number of rows and filter out as many as possible. And the goodness of your spatial index is how big you can make this number. So that's a high one. With a low one, that was 50%. With a low one over here, there's 30%, and there's no internal filter. Probably because they're all polygons that are bigger than a cell, or less than a cell. Everybody okay with that? So now you know how all this stuff works, and the new features in 2012, and now you know how to spend my summer vacation for 3 years in a row, right? It's looking at these silly things, right? Because there's no way to actually just produce a bunch of them. You have to define a spatial index and run it, and then drop it. Define a spatial index and run it, and then drop it. And I used to sit in front of the TV and watch like baseball games and just sit there and run it. Because making the spatial index takes a long time. So you can see they got quite a few things done in 2012. There's the histogram we talked about. So in 2012, there's new spatial types, new methods, new aggregates, new indexing choices, new query links for plan control, a new spatial histogram, precise binary format, and performance improvements throughout the query. Throughout the library. Is there any questions? Oh, good, because I don't know if you have a headache like I do, but remember, ready to go. Okay, well, thanks. I hope you enjoyed it, and I'll, if you're interested in all Hadoop, I'll see you at the end of the day, if we're both alive. Yes, sir.
What's missing and what's next?
What's missing?
For the next version?
3D library. Well, see, they put nothing into the next version. If he ever gets another version, they'll put in the 3D library, which everybody wanted. They'll put in, goodness, some more optimization for roads, for example. But the 3D library is bigger than that. Okay, well, thank you for coming. And maybe I'll see you this afternoon. If not, enjoy the rest of the conference. Thank you.